Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 17. In this lecture, we'll discuss the interference of one-dimensional waves. This topic is covered in Chapter 18 of our textbook by Surway and Jewett. Recall that in our previous lecture, we discussed 4 specific examples of superposition. We discussed 4 examples in which 2 simple or sinusoidal waves were combined to give us a new resultant wave with some new and interesting properties. We now want to go back to example 2 and discuss that example in much more detail. In example 2, we were discussing the superposition of 2 sinusoidal waves of equal amplitude, equal wavelength, equal frequency, but different phase constants, propagating in the same direction. So we were discussing the combining of 2 waves, wave 1 and wave 2, and note how the 2 waves are identical in every respect except in their phase constants. Using this trigonometric identity shown at the bottom, we could combine these 2 functions and write them as one function. Notice that this function has the usual sine function in it. The sine function depends on position and time, and it has a phase constant. So this sine portion represents the oscillating part of a wave, and then everything in front represents the amplitude. We now want to discuss this amplitude in much more detail. It turns out the amplitude has 2 extreme cases that are of special importance or interest to us. Notice that the cosine function here depends on phi 1 and phi 2. In general, the value of the cosine function ranges from -1 to 1. It can also be 0. If the cosine function is 0, then the entire wave is 0, and in some sense we can say the wave has disappeared. That extreme case is going to be interesting to us. In other situations, the cosine function might take its optimal values, so it might be +1 or -1. In that case, the amplitude is the largest possible amplitude. If these are sound waves that we're talking about, in that case, we would say that the air molecules are experiencing their maximum displacement. That extreme case is also going to be of special interest to us. To examine these special cases, we need to take a detailed look at the value of this cosine function. In general, the cosine function that appears in the amplitude can take on any value between -1 and 1, including 0. However, we are interested in the extreme cases. It turns out these extreme cases are the ones that find the most interesting applications in science and technology. One of those extreme cases is the situation where the cosine is equal to +1 or -1. We don't really care about whether it's plus or minus. In this context, we're really interested in the magnitude of the displacement. Remember that if these are sound waves, for example, then the wave function is telling us what the displacement of each molecule is relative to its equilibrium. And we don't really care if those molecules are being displaced to the left or to the right. We just want to know when those displacements are really big. So what we're really interested in is in the absolute value or magnitude of those displacements. Those displacements are at their biggest when the cosine function is equal to +1 or -1. When does that happen? Well, that happens when the argument of the cosine function is equal to 0, or when it's equal to pi, or when it's equal to 2 pi, or 3 pi, or in general, any integer n times pi. For example, the cosine of 17 pi is -1. Cosine of 18 pi is +1. So any integer n times pi would give us one of these extreme situations where the cosine function takes on its optimal value. What does that tell us about phi 1 and phi 2? Remember, we're talking about the superposition of 2 waves, and we want to know what phi 1 and phi 2 have to be in order to achieve this extreme case. It turns out in order for this argument to be some integer times pi, the difference between the two phase constants must be an even pi. For example, if phi1 minus phi2 is equal to 10 pi, then 10 pi over 2 gives me 5 pi, and cosine of 5 pi is one of these optimal values. A little more formally, we can say that the difference between the two phase constants, delta phi, should be equal to 2 times some integer times pi. The integer n is going to be 0, 1, 2, 3, 4, and so on. And of course, when you take the integers and you multiply them by 2, you get the even integers. So what we're saying is when the numerator is equal to an even pi, the cosine function of delta phi over 2 is going to take on its optimal value. This corresponds to the situation where the air molecules are experiencing their biggest displacement. This particular extreme case is referred to as constructive interference. We have two waves, a blue one and a green one, that basically coincide. They sit right on top of each other, they reinforce each other, and they give us the biggest possible resultant wave. This is one extreme case. The other extreme case that is of interest in science and technology is one where the amplitude is equal to 0. That happens when the cosine function is equal to 0. Of course, if the amplitude, the thing in front, is 0, then the entire wave is equal to 0. When does this happen? Well, the cosine function is equal to 0 when its argument is equal to pi over 2, or 3 pi over 2, or 5 pi over 2. Hopefully you can see the pattern here. Here what we're doing is we're taking odd numbers and then dividing them by 2. In all of those cases, the cosine function is going to be equal to 0. More formally, we can say that we achieve this extreme case when delta phi, that's the difference between the two phi's, is 2n minus 1 times pi. 2n gives us the evens, subtracting 1 gives us the odds, so 2n minus 1 times pi basically gives us an odd number times pi, something like 17 pi or 19 pi. When we put that in the denominator or in the numerator and divide it by 2 in the denominator, we get a cosine function that is equal to 0. This particular case is described as destructive interference because the two waves are destroying each other, giving us a resultant that is basically 0. So let's summarize what we've been talking about. We're talking about the superposition of two simple waves. Here I have a sine of some argument plus a sine of a slightly different argument. So we have two functions, wave 1, wave 2. Notice the two waves are identical in every respect, except they have different phase constants. When we combine them, we get this function here. Of special interest to us is the cosine function that appears in front. This cosine function controls the amplitude of the resultant. We find that when phi1 minus phi2, I've written it as delta phi here, is equal to an even number of pi's, then what we get is a situation where the cosine is equal to plus or minus 1. So we find that the amplitude is plus or minus 2a. That is the largest amplitude that this function can have. Therefore, when delta phi is equal to even pi, we say we have constructive interference. We have a situation where we have constructed the largest amplitude resultant possible. The other extreme case is that of destructive interference. When the difference between the phases is plus or minus an odd number times pi, then the cosine function here becomes 0 and we get the minimum possible amplitude. In some sense, that the resultant has been destroyed. It's not really much of a wave. It's a very trivial wave. It takes on the value 0 everywhere. So far, we've been discussing primarily the mathematics of interference. In future lectures, we'll see some important applications of the concept of interference, But for now, I do want to point to one interesting application of destructive interference, namely that of noise cancellation technology. You may have seen, or you may even own, one of these noise canceling headphones. These headphones are used in noisy environments where they can actually cancel the ambient noise. These headphones don't work by just blocking the noise. In very noisy environments, that's practically impossible to do. Instead, they use destructive interference to cancel the outside noise. So a microphone on the outside of the headphones picks up the ambient noise, and then small speakers on the inside essentially create noise that is inverted relative to the outside noise. Remember, when you take a sine function and you invert it, you're essentially introducing a phase shift. So you can invert a sine function by shifting it over by pi radians, or 3 pi radians, or 5 pi radians, or an odd number of pi radians. So now what's reaching your eardrums is actually 2 sound waves. The 2 sound waves are inverted relative to each other, or they have a phase shift of an odd number of pi radians. The 2 therefore cancel each other out, they add up to 0, and the resultant is just 0, silence. There is no displacement of the air molecules near your eardrums, so you don't experience any noise. And that is the end of this lecture. Thank you for your attention.